two sequences, say A, B, C, D, E, F, and the other sequence is 1, 2, 3, 4, 5, such that each reserves order. So for example, I could say valid in my interleave sequence, I have how many? These are 6 guys, these are 5 guys. The interleave sequence will have mandatory 11. In those 11, the only constraint is I need to have the letters in order and the numbers in order. So for example, A, B, 1, 2, C, 3, 4, D, E, 5, F is a correct sequence because both letters and numbers are in order, right? Any interleaving that swaps the order of letters among themselves or the digits among themselves is not correct. Problem number 3. 8 students, which are count student 1, student 2, they have ID, student 3 to student 8, form 2 teams to play each other. Five players each. So it will be 4 players versus 4 players. Okay. How many ways? Specifically, 2 ways are different if teammates are different. So what we call by different in this problem, teams don't have IDs. There's no team A and team B, team home and team away. There's nothing like that. The only thing different, if I play in a team with other people than I played yesterday.
Teams of 4 or teams of 5? You say?
4. 4 each. 4 against 4. This is a general problem. Could be 100, play 50 versus 50. And the last problem I want to point out is 6 men and 10 women. This is all like balls, as in they're identical. Go off the elevator on floors 1 to 5. Those floors have ID. Floor 1, floor 2, floor 3, floor 4, and floor 5. So these are identical. But the men are not identical with the women. All men are identical, or women are identical. So in how many ways can get off the elevator? So by different ways, I mean for an example of the output might be on floor 1, there is 1 man and 2 women. On floor 2, there is 2 men and 0 women. Then floor 3, so on and so forth. So an output is how many men and women go off at each floor. That's what creates different output. So I'm listing here 4 problems that the other sections did and we didn't. You don't need any special counting techniques. And some of them might show up tomorrow in the quiz. Okay? Maybe, maybe not. It's just the different counting problems. The answers are instant answers like before. You just have to make sure some of them might have a little trick that you have to be aware of. Okay? I don't think we're going to have time to it, but if you solve those problems in the next 90 minutes, you can give me the answers at the end of the lecture. Okay? So now, what we have to do here is binary and logic. Actually, it's not just binary, it's a general base representation. And we care about binary, octals, hex, and decimal, of course. Those would be our primary bases. Binary is 2, octal is 8, hexadecimal is 16, decimal is 10. But you can do numeration and representation of numbers in any base. And we talked about unsigned numbers. Unsigned means only positive. The no sign bit. That means first bit is b at the power, where b is the base. So first bit is content. It tells you something about a number. When we're going to move to sign numeration, the first bit will not have content value, will not be base at the power, will actually be plus or minus. So the first bit will be whether it's positive or negative. But in an unsigned world, we have positive numbers. So the first bit counts as 2 at the power. I think we did something here, last time. So we already know, let me see here, try to do this right. I think we've seen this table, 1, 0, 0, 0, 1, 0, 0, 1, 1, 0. This is the one that I got wrong last time, right? A few times. This is the 1 bit side, and this is 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 1, 0, 0, 0, 1, 1, 0, 1, 0, 0, 0, 1, 0, 1, 0, 1, 1, 0, 0, 1, 1, 1. Those should be 8 and 8, right? And we already know what, this is in 4 bits. I could do this in 6 bits or 8 bits. And we already know the values from last time. This is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. This is the unsigned range, unsigned binary range on 4 bits. Specifically, the range is from 0 to 2 to the n minus 1. So the integers that I can represent on 4 bits are 0 to 15.
Is that 2 to the n minus 1 or 2 to the n all minus 1?
All minus 1. So down, minus 1 is down. So because when n is 4, what is 2 to the 4? 16. Minus 1, 15. The last digit is not, the last representation, the biggest value is not 16, is 15. There are, however, 16 values. There are 2 to the n values. Because including 0, I get 16 total values to be represented there. And not today, we decided to swap the schedule a little bit. So we're going to talk about negative numbers, just not right now and not Friday, a little later. But I want to put the numbers here, the negative ones, and we save it for later why it works that way. The positive range remains the same, so this is signed. In a signed world, this bit indicates the sign, not content. So 0 will be the positive, 0, 1, 2, 3, 4, 5, 6. Let me see. This is 2, 3, 4, 5, 6, 7. However, things change in here because this 1 indicates negative. So this will be minus 8, and this will be minus 1. That's how stuff is going to work. So what happens from minus 8, I want the addition to work properly. So if this is minus 8, when I add 1 to it, in decimal, what happens? From -8 I move to where? -7, right? So mechanically speaking, 1000 plus 1 bit, I should get 1001, right? So I want from -8, when I add 1 to get -7, I add another one, I get -6, -5, -4, -3, -2, and -1. Now, we're gonna need some procedure for how to do this. And why it works that way, and we're gonna talk a little bit about that later. But for now, since we started to talk a little bit this last time, I don't want you guys to get confused into one is negative and then this is just the number that comes from there. That's not true. This is how it actually works. So then we have additions. We talked about additions. Let's take some example here. 22 is what? 22 in base 2. 22 in base 10 is, I have here 1, 0, 1, 1, 0 in base 2. Is that true? This 2 corresponds to the, this is ones, there's no ones. This is a 2. This is a 4. This is the 8, no 8. So I got a 2, a 4, and a 16. Adds up to 22. Right? How about 21? That is 1, 0, 1, 0, 1, right? So if I add those, I get 1, right? 1. 1 plus 1 is 0. And I have to carry a 1, right? And then I have 1, 0, 0, that's a 1. And then 1, 1 is 0. And I carry another 1. I get this value here. 1, 0, 1, 0, 1, 1 in base 2. And I know what I'm supposed to get in base 10, right? I know this is a 43. That's easy to see. Is this true now? What do I have here? This is a 1. This is the 2. This is the... So I don't have 4. This is the 8. And this is the 32. I can write those 2 to the 5th, 2 to the 3, 2 to the 1, and 2 to the 0. That's a better way of writing them, by the way, when you deal with numeration basis. Instead of writing 8, I think it's better to write 2 to the 3. So you know exactly this is the bit in that position. And now if you add those numbers, 32 plus 8 plus 2 plus 1, we get 43, right? So addition should work the same way in binary and decimal, get you the same value, of course. You should know those powers of 2. I think we keep going around them. What are the powers of 2? 2 to the 0 is 1. 2 to the 1 is 2. 2 to the 2, 4. 2 to the 3, 8. All is multiplied by 2, right? 2 to the 4, 16. 2 to the 5th, 32. 2 to the 6th, 64. 2 to the 7, 128. 2 to the 8, 266. That's an important one. Why? 8 bits form a byte. 2 to the 9 is 512. 2 to the 10 is 10 to the 24. That's another important one. 2 to the 11 is 2048, right? 2 to the 12. 4,096. How much is it? 496. So on and so forth. 2 to the 13 would be 8,192. It's useful to know some of this without having to compute the values. In binary, you'll need that to be fluent in powers of 2. So let's look at how numbers convert to one base into another. We're going to have a massive theorem here that we already seen last time. That's a theorem. It's called the fundamental theorem of arithmetic. That says two things that are equivalent to each other, effectively. In any enumeration base B, B has to be at least 2. Of course, B is an integer. Everything is integer here. So I'm not going to write integer, integer, integer. Everything is integers. This is the base, and n is a value. The decomposition into ak times b to the k plus ak minus 1 b to the k minus 1 plus ak minus 2 b to the k minus 2 plus a1 b to the 1 plus a0 b to the 0. This is the representation of value n in base b with digits. Which ones are the digits here? The value that you see, like 43, digits at 4 and 3. In here, which ones are the digits? Okay, so the locations, this is ak minus 1, a1, and a0. Those are the digits. When you see that number, you're going to see these values. This representation is unique. And it has the property that every digit ai is between who and who. It can be at least 0, 0 is a digit, and what's the maximum digit in base b? B minus 1. If you want to take a little bit from a different point of view, this is ai, it's a valid remainder. When division by b. So anytime you divide something by b, you get the value that the remainder is between 0 and b minus 1. And we're going to call this set very, very soon 0, 1, 2, the set of remainders up to b minus 1. We're going to call this zb, the integers that are reminders when we divide with b.
Can you remind me why you wrote unique?
Unique here,
Yeah.
meaning you cannot represent a value in base b in more than one way. If you want to write a number 8792 in base 10, let's just say 879. It's got to be exactly 879. In other words, in base 10, it's only one way to represent that number. In base 2, it's only one way. In base 16, it's only one way. In base 4, there's only one way. Now, it may seem obvious to you that that is true. It's whatever you see, right? It's the digits that you see. But mathematics sometimes is concerned with, is it really unique? Can we prove it is unique, even if it's obvious? We're not going to do that proof today, but we'll make it back to it when we do number theory later on. It says another thing which is equivalent to it, that when we do number theory, we're going to see that equivalence. The other part of this theorem is to say the division, integer division of my value n at b, right? So I take this value n and I divide with the base b, will produce a quotient and the remainder such that the remainder is one of these values, 0 smaller than r smaller than b minus 1, such that n is going to be b times the quotient plus the remainder. Right? The integer division, I'm sure you've seen this before. When you divide with some value, you get the quotient and the remainder. This is also unique, meaning Q and R are unique. So when you divide 879 by 10, let's say divide by 10, what's the quotient? And what's the remainder? 87, and the remainder is 9. Hands up who's with me. We've seen this, right, in secondary school? Division, get the quotient, get the remainder. It's that one. It's not a new one. This one is the one we've seen many years ago. So even if I come here fancy with a jacket and all that, the division is still the one from 10 years ago, right? Let's not get confused about that. How about we keep dividing this number? So I do the first division. I'm going to create a procedure here. I'm going to take the quotient that I've had and do the same. So I do now 87 divided by 10. By the way, this is a sign I made up. I'm not sure what the correct integer sign is. I don't think there is a consistent one, so everybody uses different one. Some people write 87 divided by 10, others 87 divided by 10. You know, pick your favorite. I think some calculators have this sign on them, right? So I prefer writing fractions like 87 by 10 when it's exact division, 8.7, and write this sign when it's an integer division. What do I get here? What's the quotient when I do this division? 8. And the remainder is? 7. And if I keep doing that until I get quotient equals 0, I'm going to get 8 divided by 10. Quotient is 0. And the remainder is? How much? 8. Some people, long time ago, literally thousands of years ago, recognized that this way, it's actually a way to produce the digits. If you look at this number this way, 8, 7, 9, those are the digits. And it's no surprise, those are the digits. In base 10 is the easiest base to see. We look at the number 8, 7, 10. This is the unit digit, this is the 10 digits, this is the 100 digits. So this literally is 8, according to my theorem here, 8 times power is, the base is 10. What power? 2 plus 7 times 10 at 1 plus 9 times what? 10 at 0. Right? So this is the units, tens, and hundreds digits. Now, of course, when I divide the first time by 10, this stuff is a multiple of 10, right? Because it's 10 times something. So the remainder is going to be the last digit. Now, I've got rid of that remainder, so I'm left with 87. And when I look at 87, I look at this representation, what happens to the powers of 10? The original powers are 2 and 1, so that's 870. But when I divide it by 10, what happens to this 2 and 1? They decrease by 1. So after the first division here, 87, it's very similar to the original representation. That's 8 times 10 at 1, plus 7 times 10 at 0, plus I don't have nothing because I divided by 10. So now what's going to happen when I divide again by 10? This part will be a multiple of 10 because it's 10 times something. The last digit will be the remainder. Right? So this is a general procedure that could be done in any base, not just in base 10. Of course, in base 10 it's obvious. You can guess those reminders because they are the digits, right? How about we try this stuff in base 2? How would this look for this number 8? Actually, let's try a different base, because base 2 is going to get quite a lot of values there. So let's take 879, same number. As value, this is the same exact value as before. And that's, of course, in base 10. And we want to ask, how much is this in base, let's say, 4? So we kind of have two ways to do this. The first way is what we did last time. We can guess the power of 4 that fits in. So we say, okay, what's the biggest power of 4 that fits in that number? 4 to the 2 is 16. 4 to the 3? 64. 4 to the 4? To 56. Can I multiply with 4 again, or I'm going to beat this value? So that's 4 to the 4 seems to be the biggest one. So that's 256. How many 256s can I fit in? 3, right? That would be the digit. This number being the digit, it has to be a value 0, 1, 2, 3, right? Why this number cannot be a 4 or bigger? If there be a 4, I would not have used 4 to the 4. I would have moved to the other next one, 4 to the 5th, right? So because 4 to the 5th didn't fit in, this cannot possibly be a 4. It has to be less than 4. Right? So now I got 3 times 256 plus, how much is that? 768, maybe? Right? What's the next power of 4 that fits in? 64 fits in. 64 is 4 to the 3, that's 64. How many 64s can I fit in? 1, 2. So that's 1 times 64, that's 64. And now, what else can I fit in? How much I've got so far? 832? Yeah. So how much I have left? 47, right? So this gotta be, whatever's here, gotta be 47. So what power of 4 fits into 47? 16 is 4 to the 2. How many, that's 16, right? So how many 16s fits in 47? 2 to the 16, that's 32, plus, what else do I need to put there? Do I have this in here? I think I have it somewhere. Okay, let's see. 4 to the 1, and then 4 to the 0. How many 4 to the 1s I have? And how many 4 to the 0s? 3. And this is a 3. So let's see what we've got. The digits are 3, 1, 2, 3, and 3, right? That's what I think we've got. Let's see. So this is 3, 1, 2, 3, 3. I'm wondering if I have it somewhere here. Oh yeah, I have it. That's the one. All right. So we did it this way by taking our powers of 4 and keep going. How about we do the division algorithm? That's the one that we did here for base 10. How would that work out? 879 divided by 4. What's the quotient? And what's the remainder?
2,973.
If you believe this stuff, if you already know it's 3, 1, 2, 3, 3, you wouldn't do it again. But if you do, you could do exactly the same thing that you did with those digits here. The first remainder is the last digit, right? So what's the last digit? 3. I bet the remainder here gotta be 3, because this will be the last digit. In other words, if you look at this stuff, 4, 4, 4, 4, this whole stuff divides with 4, except for the last one. So when I divide by 4, I'm going to get a quotient that's exactly 3 times 4 to the 3, because I'm dividing by 4, plus 1 times 4 to the 2, plus 2 times 4 to the 1, plus 3. That will be my quotient. And then the remainder is be the part that does not divide by 4, is this 3 at the end. So what's the quotient here in decimal? How much?
2,973.
It's got to be 200 something, right? Because it's 800 divided by 4. 219. Okay? I bet that 219 is exactly 3123 in base 4. Just like 87 was the first two digits when I divide it by 10. If I transform 219 in base 4, I wouldn't be at all surprised if I get exactly this guy here. Right? Because, think about it, isn't this 3, 1, 2, 3 in base, this is all base 4. Isn't this times 4 plus 3? In base 4, the same way 879 was 87 times 10 plus 9. This number in base 4 will be 3123 times 4, the base, plus 3. So when I divide with 4, this will be my quotient, that's in base 4, and that will be my remainder, right? Hands up who's with me. You can verify that, it's 219, exactly that representation in base 4. But let's keep going with the division here. 219 divided by 4. Now, what's the quotient?
54.
How much?
54.
And the remainder?
3.
Then 54 at 4 is 13. Remainder? 13 at 4. Quotient is 3. Remainder is 1. And now 3 divided by 4. Quotient is 0. That's when I stop. And the remainder is a 3. So now if I read this, the reminders obtained are backwards. So 3, 1, 2, 3, 3. I get my number 3, 1, 2, 3, 3. That's the same like in base 10.
Why is it 52 divided by 9?
54. Very good. Okay. So I got 3, 1, 3, 3 in base 4. How about I try to do this in base 16? 879 divided by 16. I get what? Now it's a little harder because we don't have the reminders already. In a base 4, we know it's going to get 3, 3, 2, 1, 3 exact. So what's easier? But what happens if I divide by 16? I get 54? No. So the reminders I need, I think it's, I have it here 15. And the quotient is 54. Okay. So 54 divided by 16. I've got a reminder 6 here. 6 out of 54 is 48 now. Divide by 16.
3.
And then I've got 3 by 16. Quotient is 0. That's the stop. I know I'm done here. And the remainder is 3. So according to this, I've got 879 be what value? 3, 6, and 15 in base 16. Base 16 is called hex. So when you see hex, that's base 16. Base 2 is binary. Base 8 is octal. The thing with this 15, I don't want to be confused with the digit 15, which is certainly valid in this base, right? It's the biggest digit in hex, 15. But I don't want to write it as 15 because I'm going to get confused with when it's 15 and when it's 1, 5, right? Let's be clear, the digit 15 is not the same as writing 1, 5 in hex, right? 1, 5 in hex is what? F. That is F. This is the digit F. But if I write 1, 5 in hex, what do I mean? 1 times 16 plus 5. So this is not the same thing. When you write 115, you mean the units digit is 5 and the tens digit in is 1 in base 16. So it's 1 times 16 plus 5. So then we need to replace those with something else so we don't get confused. This is F. And what are the others? Right, E, A, B, C, D. It's just a notation, so it's nothing fancy about it. I don't want to get confused between, I don't need to replace 9 because I wouldn't be confused about 9, right? Only the ones that have values 10 or bigger. Okay, what about if I try the other way here with binary? What if I say I want A79 to play out this power game? How is that going to come out? What's the biggest power that fits in? 16 squared is 2.56. We already done this. It fits in 3 times. Plus, I already know I need a 6 here. 6 times, that's going to be probably 16. Right, 16 at 1. Plus F, which is actually 16 to the 0, right? So that's 15. So 256 times 3, we already said is 768. Plus 16 times 6, how much is that? 96. Plus 15, does this check out? Is this 879? Is it? All right. So again, 2 ways to get numbers from decimal into hex into base 4. We can also do base 8. Let's do base 8 quick. 879. We do division by 8. What's the quotient? And what's the remainder? I think the remainder is 7. And the quotient I've got here is 109. Sounds right to you? 8 times 109 is 872 plus 7, right? So then I get 109 divided by 8. I get 13, remainder 5. Then 13 divided by 8. I get 1, remainder 5 again. And then 1 divided by 8. I get 0, remainder 1. So now if I read it backwards, I get 879. It's got to be 1557 in base 8. So I've got this number 879, base 10, base 16, base 2, base 4, base 8. How about base 2? If I do this in base 2, what we're going to get? I could do, in base 2 is no different than the other bases. The only easier part in base 2 is that the digits are only 0, 1. So I don't really need to put the digits in front of it. If I put that power, is digit 1. If I don't put the power, it's digit 0. So how much will be A79 in base 2? I'm going to try to kind of shortcut in here. I'm going to say, if I already have base 4, I can try to map out base 2. So how do I do that? I got 256 to fit in, but in base 2, if I multiply 256 again, what do I get? How much is that? 2 to the 9. How many times that fits in? In base 2, if it fits only once. Because the digits gotta be 1, right? You can't fit more than once. Otherwise, it will be the next power. Plus, so this 2 to the 9 covers the 256 times 2. What would I get next? I get a 2 to the 8. Would that fit? 256. Fits again. I know it fits again because I know there's 3 256s here. 2 are the 512, and the remaining one is the 256 power of 2, so that's 2 to the 8. How about the next power? Will be 2 to the 7, right? How much is 2 to the 7? I know that doesn't fit. Does it? This is 256. So the sum is, we already have it as 768. I don't think 128 fits in. So I don't have 2 to the, this 0 times, this is 1 times 2 to the 7, so that's 0. What else I have? I have here 2 to the 6, that's a 64. I also have a 2 to the 5, that's a 32. I'm missing the 16, and I have the other ones. So that's the 16 missing 8, 4, 2, and 1. So if I read this as a binary representation, it will be 1, 1, 0, 1, 1, 0, 1, 1, 1, 1. Okay? I don't want to do it, but I could do exactly the same thing if I do the repeated division, and I'll get the digits. The first division will result in a 1, then another 1, 1, 0, so on and so forth. I get all that. What I want to point out here is that some bases are very related. So now, arithmetics of bases. Arithmetic of bases. Things like 8 is 2 to the 3, right? So a digit in base 8 is equal with how many digits in base 3? Or corresponds to? I shouldn't say that, I should say, let's say equal. 3 digits. That's because of this power 3. So to show you that, I'm going to take that number in base 2. So, sorry, base 2. 1, 1, 0, 1, 1, 0, 1, 1, 1, 1. And I start grouping the bits from the end. So I'm going to make groups of 3. From the back, from the right. So here's the first 3 bits. Here's the next 3 bits. Here's the next 3 bits. And here's the next 3 bits. What is this value in base 8? 7. What is this value in base 8? What is this value? And this one? So guess what I've got? I got exactly this number in base 8. 1557 was the base 8. No surprise, because every 3 bits in base 2 make a bit in base 8, because 8 is 2 to the 3. Right? How about if I take the same number and I make groups of 2 from the right? So who is 2 to the 2? 4, right? So if I do groups of 2, I should get the representation in base 4. Let's write it again. 1, 1, 0, 1, 1, 0, 1, 1, 1, 1. Groups of 2, 2, 2, 2, 2. So what do we get? 1, 1 is how much? Base 4. 3. 1, 1, 3. 1, 0, 2, 0, 1, 1, 1, 1. Did I get exactly the representation in base 4? How about in base 16? What would I have to do in base 16? It's 2 to the 4. Let's write it again. 1, 1, 0, 1, 1, 0, 1, 1, 1, 1. We want groups of 4 from right. So here's 4, 4, 4. So how much is 1, 1, 1, 1 in base 16? F, which is also 15. 0, 1, 1, 0, how much is that? 6, because it's 2 to the 2 plus 2. And 1, 1 is 3. 3, 6, F. Is that what I've got here? 3, 6, F. Somewhere here, right? 3, 6, F. So that's the way I can convert among those bases. It doesn't work with base 7 or base 9, but bases that have this property, one base is the power of the other base, would definitely work this way. The exponent will tell me the power, how many digits I need in this base to make a digit in this base. So something for you guys to think about is, what if I want to convert, how about from 16 to base 4? What's the relationship there? Is it a power relationship between 6 and 4? It's 4 to the 2, which tells me if I write in base 4, what was it in base 4? This is in base 4? So if I write it in base 4, 3, 1, 2, 3, 3, how do I need to group the bits to get base 16 now? 2 at a time, right? So how much is 3, 3 in base 4? 15, that's F. How much is 1, 2 in base 4? 6, and that's the 3. So I get the representation base 16, because 16 and 4 have this property of powers. That's all very good. How about from base 8 to base 4? What's the relationship from octal 8 to base 4? Is there a power relationship? Is 8, 4 at some power? Right, it's not the power, it won't be an integer. So, can I still do something like that? I can't say that many bits in base 4 make a bit in base 8, because that many won't be an integer. But I can say 3 bits in base 4 make how many bits in base? Would that be correct? 2 bits? I should say digits, because bits are only in base 2. Would that be correct? 2 digits in base 8 make 3 digits in base 4. The overall power of representation, 8 is 2 to the third, and if I have 2 digits, I get a 2. This is 2 to the 2, and if I get 3 digits, I get a 3. Is that working out? Right. So that's an exercise we can try. Take a representation in base 4, where is it? 3, 1, 3, this. And then say, for every 3 digits in base 4, I'm trying to make 2 in base 8. Right? That should give us the answer. So that's what I have to say about numeration basis. And there's a lot of addition exercises that you can try. And soon we're going to have also subtraction exercises. Let's try to do something in base 4 here. 105. Let's do maybe this one, 879. So 879 in base 4 is 3, 1, 2, 3, 3 in base 4. How much is 100 in base 4? 64 is the biggest power and fits once, so that's the 100 digits, that's the 64. What else I need? So how do I do this in base 4? So 64 times 1 plus 16 times how many? 2 plus 16 to the 0, that's units times, wait. So 64, I get 16, 2 16s, that's 96, right? So how much do I need? 1, 4 plus 0, right? So the number will be 1, 2, 1, 0. So this is the units. This is a 4. This is 32. And this is 64. So 64 plus 32 plus 4, right? So if I add them up, what do I get? This is addition in base 4, right? 3 plus 0, 3. 1 plus 3 is 0. Keep 1. 2 plus 2 plus 1 is 1. And keep another. 1 plus 1 plus 1 is 3. And this is a 3. Can anybody, I'm supposed to get 979? Is that true? So the addition, if you understand base 2 and base 10, will work the same in all the other bases. The most important part of additions is when you do a quiz or a homework or an exam is to have some verification for yourself. Right? So what you want to do is to do it in the way that feels more comfortable, the way you are sure. But then if you have time at the end of the exam, go over it, and like with everything in an exam, try to do it in a different way. So don't do it the same way. If you have 5-10 minutes, say, okay, I've got this addition, how can I verify it? Try to do it in a different way. And then if you get the same answer, that's a strong indication. If you are lost in those bases, always try things like, if I add, how much do I need to add to this to get the power of 2 or 4, right? So every time you relate numbers, so I'm in base 4, every time I relate to a power of 4, that would be what power of 4? It's close to here. So it's 256, it's 4 to the 4 to the 5th. 1024, right? So I can ask how much I need to add here to get to 124, which is a very convenient power. It's 4 to the 5th. So that would be 100000, right? With 5 zeros after it. So that's an easy way to verify my calculation. Now, of course, if you have a calculator, and calculators are allowed, some calculators have numeration bases that you can plug in and get the answer. But I'm pretty sure when you get the calculation, you won't be allowed to use calculators, right? We'll be back in 2-3 weeks at this to deal with negative numbers. Before then, we have to talk about logic and gates, which is very related to binary. Today we do a lot of simple things in order to give you everything you need for the homework, the written homework. And then we'll have some time Friday to talk about fewer and more interesting things. So logic and logic operators. So in here, variables are Boolean or logic. So variables could be A, B, C, D, could be X, Y, Z, T, could be capitals A, B, C, D, could be P, Q, R, all those names. You have to be clear when you write or when you read something. Is big A a set, or is it a variable, or what is it? I know it's confusing sometimes because we use those names everywhere. So if they're Boolean, there's only 2 values. The value true, which sometimes we say it's 1, sometimes we just say true, sometimes we say yes. And false, there's only 2 values, which is 0 or F or no, depending on the context. But there's only 2 values. And so if I look at the variable here, A, I have only, this is a truth table. Truth table is kind of a brute force. I'm listing all variables for A. A could be true or false, right? That are the options. And if I have another variable B, that could also be true or false. Now, how many possibilities I have there? A could have true or false, B could have true or false. So how many possibilities? I have 4, right? 1, 0, 1, 1, and 1, 0, 0, 0. Because there's 4 possibilities. What if I add a C? How many possibilities I have now? I have these possibilities for C, 0, 0, 0, 0. And I have, again, those possibilities. 1, 1, 0, 1, 1, 0, 0, 0, 4, 1, 1, 1, 1. it's no surprise that this is 2 to how many variables there are. So there's 2 to the n possibilities, if there are n variables. Because the possibilities are independent, and we apply the product rule, 2 possibilities for A, 2 times B, 2 times C, so then for C, and then I get the possibilities is 2 to the how many variables I have. So the operators, the basic operators, are, I'm sure you've seen them already, and as in logic and, which we call, has a funny sign, this sign, or it's the other one, not is this one. And associated with these guys, there is also another notation for the same thing, which for unknown reasons we insist that you learn. I never learned this stuff until I taught this class, and I was a very successful computer scientist before, but nevertheless now I learned this stuff. So it's just another way of writing it, okay? Because people who build these circuit boards, they like it in a different way. So you should know it's the same. This could get confusing, like this is a way to write and, this is a gate. This is English, this is logic, and this is gates, okay? Here's the OR one. So you're gonna have a lot of fun trying to not draw them the same, like me here. And here's one that's not. It's easier. Just put a circle. Every time you see this circle, that's a not thing. The reason they have a bunch of inputs is how many things you end or not or ors. So for not, it's one thing, because when you say not, so let's see what we get here. If I want to say who's not A, I'm pretty sure everybody knows that not 1 is 0, not 0 is 1, not 1 is 0 again, not 0 is 1, so on and so forth, right? What if I want to say A and B? What happens to that? 1 and 1? 1, right? Do we know the stuff from before? 1 and 1 is 1, and is like intersection. You can, in the sets notion, you can call this an intersection. Because when you say and is in that set and that set. And 0, 1 gives me a 0, 1, 0 gives me a 0, 0, 0 gives me a 0. How about A or B? When do I get 0 in OR? When both are 0, right? 0, 0 gives me 0. The other ones give me 1s. So this is more like union, and this is more like complement. And we have other gates. We have XOR. Exclusive. So this is like symmetric difference. I don't think there is a sign for XOR, but there is a gate. There might be a circle with a plus in the middle.
Isn't the delta? I think it came out of recitation.
It could be.
It's like a triangle.
XOR. So this gate here is like an OR, but it's doubled. So that's a XOR gate. Then we have a NAND, which is not AND. This is not A and B. So the NAND gate, it's simply an AND gate with the negation This is the negation here. And then there is a NOR gate. Which is the end, this is not A or B, not OR. So in here I got the OR gate, and then negated. Okay, so how do I do stuff in here? I'm gonna cover this for a while and then uncover them later, because I want this table here. So if I have A and B, 1, 1 is 1, 0, 0, 0. I can start building more complicated stuff. Like suppose I want A and B that I already got here, or C. How do I do that? So I've got A and B, I've got this column, and now I do or C, right? You see the parentheses? There's precedence here, just like multiplicativity and addition. Sometimes if I don't put them, there's a certain order in each stuff happens. My recommendation for you, just put a parenthesis, okay? So we don't get confused about it. The only one that doesn't need a parenthesis is not. Not A happens first. So not A or B, it's not the same as not A or B, because the negation happens first and then the OR. If you really want the OR to happen first and then the negation, you have to put parentheses over the OR to indicate the OR happens first, then the negation. Otherwise, negations would apply first. So how do I do A and B or C? I could do it directly for A, B, C, or I could do A and B or C. So if it's 1 or 0, I get 1. 1, 0 or 0, I get 0. 0, 0, 0. 0, that's the first 4. That's the dotted line tells me where I am in the table. And then in here, A and B or C. Now, C is 1. So anything or 1 will be 1. Let's write that rule. 1 and anything or true is true. 1 or any is 1. For 0, how the stuff looks like. 0 and anything is 0, or false anything is false. So when you have a false and something, that results in false. What about, this is something I think we're going to do a little later. Maybe we have some formulas here. Yeah, we're going to do them later. What about if I say A implies B? What do I really mean by that? So if I'm to build a truth table, I know it's not right now, there's some other things with sets and stuff. What do I mean for A, B? If I want to build a truth table, how would that look? What are the possibilities for A and B? 0, 0, 1, 0, 0, 1, and 1, 1. Every time you write possibilities in a truth table, just write all of them. Don't complicate yourself with I'm writing the 7th ones that I think are important, I'm left out. Don't do that. Write all of them. So I'm building a truth table for A and B. I write all 4 possibilities. Now, when is this stuff true? When A implies B? Yes.
If A is true, B is true.
If A is true, B is true, this is true. Now the implication itself, it's a statement that could be true or false, right? So how about 0, 1? Is that true? 0 implies 1? That's why we need to save it for Friday to discuss that one, right? This is what everybody's gonna freak out. That's true. 0 implies 1. Save the freaking for Friday, okay? We're gonna have more time then. How about 1 implies 0? That's easy. 1 implies 0, true or false? False. That's false. Let's make sure. How about 0 implies 0? True. So I can keep going with this stuff, and then I can build it even further, right? How about if I have A, B, C, right? How many possibilities are here? 8. And then I write A implies B, everything implies C, right? Which should be easy because I still get to, I first get A implies B, is that true or false, right? And then how many possibilities for that are just the ones in here. And then I get C, true or false. Only 1 implies 0 is false. Everything else would implies is true. 0 implies everything, and 1 implies 1. The only stuff that's incorrect or false, it's 1 implies 0. So what else can I do with this with these quantifiers here? Well, I could relate to sets notation. For example, when I say here union, I could say A union B, right, is the set of elements in set builder notation X with the property X in A. That's a statement. That's a logic statement that could be true or false for an element in a set, right? Element could be in the set or could be not in the set. And what logical operator do I need here? Or X in B. That's also logic. So you can see what's going on here. For an element to be part of this set builder notation, this has to be true, 1, or this has to be true, 1. Otherwise, it's not, the whole thing is not true. So as a predicate or as a statement, this will be true when either one of them is true, which corresponds to our definition of intersection from before, right? How about the intersection? A intersect B is the set of the elements, of course, that are in there. And what do I need here? And so when would this one be true? For this one to be true, if you look at end table here, where we have end, when is end true? Only when both are true. So for this to be true, I have to have X in A and X in B, which again corresponds to our notion of intersection. So how about bigger formulas, right? Let's try to build this table further. I mean, you probably want to write the ABC again. I'm not going to write again, but you can write the ABC, all those 8 possibilities here. And suppose I want to get, I already have A and B. How about I get A and not B? Right? How would that look like? A and not B. It's not very different. A and not B. So 1 and 1, what do I get here? I get false, right? Because not B is false. 0 and 1? 0. Actually, when is this thing going to be true? Let's do the faster way. I need A to be true, or 1, and B to be false. So not B is true. So when is that going to happen? A is true and B is false. It's going to happen here. 1. And where else is going to happen? This configuration, A true, B false, appears again here. So there's going to be 0 here, 0, 0, 1, 0. And I can do now A, C or not A. Not A and C. Again, this is we can do it the same way. I need A to be false and C to be true or 1, false is 0. So where is that happening? C false, it's here. No, sorry, C has to be true. So it's in this area here. C has to be true. And where is A false? Those two. It's normal to have, why there's got to be two possibilities when this is true? If there's one possibility for it to be true, there's got to be another one possibility in this table. Why is that? Yes?
This one portion B is one and one with B.
If it happens to be true for a particular B, then for the other B it will also be true because this expression does not depend on B, right? So those two cases I think are here when A is false and C is true, right? So they are the 0, 1, 0, 1. This is 0, 0, 0, 0. And now suppose I want to build a bigger expression, A and B, or A and not B, or not A and C. Now, of course, I've just built those three parts. I've got A and B here, I've got A and not B here, and I've got not A and C here. So those are my three parts here. So I'm going to do, and between them I have an or, right? Or. I could do it one by one, but to speed up things, if I have an or of three things, what do I need to get true? One of them to be true. So now I'm looking at, I'm ignoring this column because this is not part of my formula, right? It's this one, and this one. So when is this going to be false? That's the easiest way to think about, right? Or. There's not that many cases going to be false. False is going to be exactly when? 0, 0, 0, right? So now I'm looking my trees, this and this and this column. Where is 0, 0, 0? The second one is 0, 0, 0? So the second one, it's a 0. How about the third one, the last one here? So this is 0, 0, right? So this is 0, 0, 0. How about in here? Do I have a 0, 0, 0 in here? This is 1, 0, 0, 0, 0, 1, 0, 1, 0, and 0, 0, 1. Is that a 0, 0, 0? No. That means these guys are going to be true. Who's with me? This is easy stuff, right? I mean, this is, maybe you were thinking, oh, the class is too hard so far, right? So there you go, it's not that hard. I mean, some people complain, I think, rightly so. I think homework was a little bit of a stress. And then we've been, somebody suggested that, hey, maybe you guys doing too hard. But not to me, they say you can do whatever you want. So you guys in here have no excuse. They have 600 students, they have excuses. But in here, it's, you know, nevertheless, this is easy stuff. So I've got the big formula here, which I can build from parts. I can also manipulate. I have a bunch of rules here that I'm sure you've seen before that allowed me to manipulate these not in terms of truth table, but in terms of some logic algebra, so let's call it. So like we do operations with algebra, we can do operations with these operands here, or, and, XOR, so on and so forth. So I have these rules that says P and Q is the same as Q and P, obviously. Every time we're not sure whether a rule is true or false, how do we check it? Yes. Build a truth table, right? What does it mean to check out? I build it for, I want to say it's equal, I'm not sure, right? So how many options are for P and Q here? 4 options, 0, 0, 0, 1, 1, 0, 1, 1. I build this one, P and Q. What is that? 0, 0, 0, 1. What is Q times P? P times Q is the same, 0, 0, 0, 1. How do I know they're the same? They have to be identical. The same means the same all the time, no matter who is P and who is Q. So since I have all possibilities here, that's how I check it. Now this one we don't need to check, it's obvious, but some of them may not be so obvious. So that's the same for P and Q is the same as Q or P. P or Q is Q or P. Now, this is not really the valid sign, so I would say okay for computer science. In mathematics, they use a different symbol. As far as I'm concerned, if you mean the right thing, that's what matters in this class. But as you progress towards more math, say more theory, you're going to be required to use the proper symbol. They use this symbol, the same logical equivalence. So I don't think we're going to take off points if you put equal in there. But what we really mean is logical equivalence. What else is obvious? Can I say P and Q are is and P and Q and R? Is that true? If I end three things, can I end them this way and then with that, or that way and then with that? Where would this, now common sense, where is this is 1? There's only one case where this whole thing is going to be 1. When everybody's 1. Doesn't matter which way we end it. Right? Same for ORs, right? This is the obvious stuff, like everybody could guess. How about this distribution? If I have P or Q and R, just like multiplication distributes over addition, do you think this is P or Q? So this way, and then and P or R? Can I distribute one logical variable, distribute the or across both of them, Q and R, and leave the and in the middle? Would that work? If I'm not sure, what do I do? Check the truth table. How about the other way? And Q or R, is this P and Q or P and R? Right, distributing now the and over the or. Again, I think it's true because it's written here, so it gotta be true. But if you're not sure, don't trust me. Build a table and check it out, right? Can I distribute it over three things? How about Q and R or T? Can I say this is P, is an and here, and Q, or P and R, or P and T? True or false? So everything I wrote here on the board are questions. I'm not saying they're true or false. It's your responsibility to go home, build a truth table if you're not sure, and check it out with the truth table for all those formulas. If you are sure, you don't have to build a truth table. If you're not sure, build a truth table to verify it. So I have some other ones. There'll be a big table at the end. What happens if I do P and P? Can I say that's just P? Which is the same as P or P, because or and ends with itself doesn't change the value. 0, 0, 1 and 1, they produce the same value, right? How about P and P or Q? What is this? Common sense. What does it need to be true here for it to be true? P. Right? If P is true, the whole thing is true. If P is not true, the whole thing is not true. Same thing if I say P or P and Q. That's P. And then there is this particular category of things, De Morgan, which is, if you want to negate P or Q, that's very important in logic when you have to build proofs, you know. if the theorem says he's either rich or old, how do we negate that? What does it mean to negate either rich or old?
He's not rich and he's not old.
Right, so we need what? Not P
Okay.
and not Q. And if I say not P and Q, he is rich and old, negated. How that looks like? Not rich or not old. All these laws have names, like there's names here. I've never been able to remember the names. I don't expect you to. If you do remember them, please in an exercise, homework or exam, write the name. There might be a question that specifically say apply the Morgan law to do something. Then you have to apply these laws. This has an important equivalence for sets. What is the not for sets? Complement. So for sets, how would I do not P or Q? If I have two sets A and B, the OR means union. So here's the union. If I say complement, I'm going to say complement, right? Complement means the universe minus that set. So this rule says the complement of A union B, what is this? How do I translate this into sets? Is the complement of A, this N means for sets, intersection with the complement of B. And the complement of the intersection, the other law, is going to be the union of the complements, right? You can verify this with some Venn diagram. Here's my universe. Here's A, and here's B, and I take the intersection. What's the complement of this intersection? It's everything in the square except the intersection. Is that the complement of A, union of the complement of B? If I do this part, do I get everything in the square except the middle part? Right? So that's the De Morgan laws. So now applying those laws, I can do something here with the derivation. Again, you probably want to write this again. I could say simplify this formula with those laws. So I'm looking at this formula here, and I'm doing a logic derivation, or I'm doing a logic algebra. So how can I manipulate this using some of those laws on the board? I can look at the first two and say, is there a law that applies here? I would say if there is a law that will give me here A or B, A and B or not B. Is that true? If I distribute the A over this parenthesis, do I get A, B? That's the first parenthesis, and the A not B, the second parenthesis, and the OR in the middle becomes this OR here. Who's with me? This is just a law, one of these laws that we do the distribution here of the AND over the ORs. And I still have, this is one part, and I still have that, not A or C, right? Now, B or not B is 1 or true. A and true is A, or not A or C. So now if I apply another rule that says or, you can move the parentheses around wherever you like, right? There was a rule that says if you have 3 ors in a row, you do it the last two or the first two is the same. So I say A or not A.
Yes.
Did I make a mistake?
And non or
Hmm?
It's
Not
not
A
A
and
and
not A or C.
Far right.
And. Sorry. So then I can't apply that law. What do I do here? I can distribute, now this is a distribution law, I can apply the distribution A or not A, and, or, and or. So I apply the or, A or not A, I get here, A or C, I get this one. How much is this? True, true, and anything, it's A or C. So I can simplify this logic formula to get to here by applying all kinds of manipulations. Now, if I'm in an exam, how do I verify that those two are the same? I have 5 minutes. What should I do to verify that those actually is the same with this? No matter the value ABC, you get the same answer. Build a truth table and verify that whatever you get here, you also get here. Always when you verify, you want to do it in a different way to see if you are right. The fun part is when you get a different answer with truth tables, and then you have to find where is it that you got it wrong, right? Because the problem says you got to use algebra derivations, so you can't just put a truth table, you got to fix the algebra derivation, right? And you only have like 45 seconds left, right? I want to show you one more thing here that relates to these gates. So I can combine, I can do the same kind of logic just with gates instead of formulas. So we have the truth table, and we have the logic operators, and we have the circuits. So if I want to do this formula here, another one, not A and B, and A or not C, right? If I want to do that, I can build a truth table for it, right? I can be like A, B, C, how many possibilities are there, da 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 da, it's 8 possibilities. And then I apply the formula A and B, and A or not C, and see what happens, and I get a value. Or I can build a circuit of gates. So here's how I'm thinking to build that. I'm building it part by part. Here's A, and here's B, right? And I have an A and B here, so I build the AND gate, right? That's the end. And now I build this part A and not C, so I kind of get a wire. This is an electrical wire, so whatever current, if it's current in a wire, that corresponds to 1. No current corresponds to 0. So I build another wire here. I need a A or C, so that's the C here, right? This gate is the OR gate. This is an AND gate. This is the OR gate, A and not C. But I didn't draw it right because I need not C. This is C, but I have in my expression here not C. So what do I have to do? Put a NOT gate on before I enter this OR. I have to have a NOT gate, right? So I put a NOT gate here. And now who's on this wire here? This wire is not C, right? Who's on this wire here? A. So this is A, B. Who's that coming out of this wire? A and B. Who's coming out of this wire? Now what do I have to do with those? I have to end them because this end here is this gate, right? So who's going to be coming out of this wire? A and B and A or not C. So what do I have to do with this? I have one more operation to do to this whole thing, the negation, right? So how do I do negation? I build a negation gate, and that's my formula. Okay. Makes sense? So you can take any one of those formulas, build the gates piece by piece, and you go for the smaller piece first, just like with operations in arithmetics. And then that's another smaller piece, then you move to the next operand, and you build another gate. And if I have A and B and C, I could make one AND gate. Instead of doing, I could do A, B, C, and that's sometimes allowed. You know, instead of building A and B first, the gate, and then the result and C, I could just end all three of them, or all three of them. So there's more circuits. I'm not going to insist on them, but they might show up in not this quiz, because this quiz doesn't cover logic. The next quiz or homework. So you may want to check more circuits examples. The last thing I want to do is to show you a particular sort of formula that's very important in computer science theory. The logic formulas, they're not different than other formulas, but they have a DNF formula or form. It's something that's ORs. So it's or, and inside it's only ends. So this is ends inside. And negations. So for example, this could be, as an example, A and B and not C. That's called a clause. And then I have a big OR. That's the next clause. B and D and not A. And then I have another clause that says A and C. So the principle of these formulas is that between the clauses we have ORs, and inside we have only ends, and the literals could be negated or not. The other one, that CNF form, is the opposite. There's ORs inside and ends outside. So that would be A or B and A or not B and not D and, sorry, that's ORs here. B or C or not D, so on and so forth. This is a CNF formula and this is a DNF formula. And you have to know how to get this from a table, which is pretty obvious. If I want a DNF formula, how do I look at the truth table and figure out the formula from there? Look at the big table with A, B, C, D, all my literals, and say, how do I build the DNF formula? I have to compute all those clauses separately, the clauses, and I say, this formula will be true where? Where either one of these clauses is true, or maybe it's easier to say when the formula is going to be false. When all clauses give me false. And how about this one? I build the parts with the truth table. I build those parts. When is this true? When all classes gives me true, the rest must be 0. So from a truth table that has not just ABC, but the clauses built in, I can very easily look at the results and say, when you get 0, 0, 0, you got to get 0. Everything else is 1. This is when you get 1, 1, 1, you get 1. Everything else is 0. Anybody has any solutions here? I would do these problems before the quiz, because they might be in there. I think they probably in the website, some notes from the other professors, the regular sessions, they spend no time on Catalan, but these problems are in there. The interesting ones, you get the two ones? Yeah. How much is that?
That's gonna calculate.
No. Just a combination. Right, because it's like you have 11 symbols when you put the letter.
I have we had a
How about the one, two things?
This is that song. Like, and it's the C, like it's like it's
symmetry. Right? Doesn't matter. How about the last one?
all those things that you work are those also true, right? And I said, like, it's now I'm like really like I don't want to do that. I don't want to go back and check them at all.
It's 5, 4, 6.
I need one up there that was only true in one
Or
specific.
sorry, 5 minus.
So like, also I didn't see why they were an XOR gate because you didn't expect. How does symmetry difference go into true or false? It's the symmetry difference is all the stuff in one that's not in the other. Is that it? So
one or the other, but not. So like, if it's two zeros, then XOR is
oh, yeah,
if it's
that's
zero, then it's 0 and 1. But if it's 1 and 1,
That's because there's only one way of
I think some of these answers are in the
Why didn't you just
IQ
follow me?
notes from last week.
I try not
But the regular section, lecture notes,
Different, like if
the
the
problems
last
are in the
person
notes.
had an idea of like,
No, it's
question?
Yeah, two different sets of numbers, is it both the same for 5 bins?
Yeah.
Like you have 8 and 2 bins.
didn't you do
No, because the students have IDs. Balls into beans, you have to have the ball beans. Here, the students, clearly listed student 1, student 2, student 3, right?
I just
So if you play the
multiplied
same
10
team with me,
choose
it's
four
different
by
if you play
13
with her.
choose 4. So it's just, you just multiply the two separate balls each 2 minutes together.
Oh, I don't know, but that's not a balls into beans problem. That's just, how do you choose the team of 4 out of 8?
Yeah, it's, I think,
The only thing is you gotta be careful, the two teams are,
I just checked
two
the
teams have
Is
IDs.
it 8 choose 4?
I mean like 10 choose 5,
They choose 4
11
divided by
choose 5 or 6. You choose 4 over
When
2.
you choose a team, the remaining 4 are the other team. Now the issue is you choose it twice because you choose for team A, team B, but the teams don't have IDs.
that's 11 choose for it.
Divide by 2.
Divided by 2.
Because every way of partitioning into 2 groups have been counted twice. Right? Every time you take students 1, 2, 3, 4 to form a team, and students 5, 6, 7, 8 are the other team, that you counted that. But then later on you count 5, 6, 7, 8 to be
Are there 10 women or 5
chosen,
women?
and 1, 2, 3, 4 to be the other team, which is the same.
Yeah, there's 10 women.
Yeah.
The teammates are the same.
Okay.
Or the other way around. It doesn't matter.
That does make sense, okay.
You guys have to recap counting before your quiz, because
Yeah.
binary and logic is not in the quiz,
Oh,
okay?
that's good. Thank you.
Are any like extra things like Howland, like those aren't choose?
What?
Or is like Howland numbers on the quiz?